Cubic modeling. So cubic models are in the form of y equals ax cubed plus bx squared plus cx plus d. Just like before, d, the final constant term, is the value of the y-intercept, because at the y-intercept x equals 0, and so on. So in the space below, draw a sketch of this type of function and write out its general equation. Go back and see page 3 and 4 of your booklet if you're not sure. So remember the general equation I've just said before, it's ax cubed plus bx squared plus cx plus d. D is the value of the y-intercept, just like the other functions. So a general sketch, feel free to use a ruler if you want, looks a bit better than what I just did. X and y, there's different forms. So you kind of get ones that are like this. Oh gosh, no, it's not meant to look like that. Something's kind of a bit up with the board. I don't know why this happens sometimes. Happened again. It doesn't have that funny divot in it. I don't know why this is happening. As I said, maybe if I do this a bit, bring it back to life, change pens maybe. Oh, this is so annoying. Okay, I'll just quickly pause the video and close and open it again. Great, okay, so I just opened and closed it, so I just have to scroll down. So generally, these ones are in the form of like this. They kind of have a little thing in the center, this little point here. It's called a point of inflection. Slightly different to a turning point or a vertex, because remember at a vertex, it kind of goes up and then down, or it goes down and then up. But for a point of inflection, it goes up and then continues up, or it goes down and continues down. That's a type, general kind of graph that the function that would kind of match something like that would be y equals x cubed, where notice there's no other bx squared plus cx. There could be a plus d at the end, so you could have a constant term, it just shifts it up and down vertically. But if you kind of have values of b and c kind of being not 0, you kind of end up with different kinds of graphs. So you can get cubics that look like this. So notice they go on kind of infinitely this way and that way. So that's one type. So notice you've got two vertices. You have a maximum and you have a minimum. So that's a minimum. This one's what we call a maximum. Whereas quadratics either have just one minimum or one maximum. So we've got, do one more example, just so you get the hang of it. You could also get them kind of going like this instead. That kind of thing. So see, same thing as well, you've got a maximum here, and you have a minimum here. So when you have values of b and x that are not 0, b and c that are not 0 in that general equation above here, so values of b and c that are not 0, that's when you tend to get these kind of more roller coaster looking ones. Whereas when you've just got x cubed plus a number, or x cubed minus a number, you just get like the first form where you've got the point of inflection instead. Cool. So what are some features of this type of function? Let's see, what's this domain and range? Domain, have a look at those graphs. Do you agree they're going infinitely out in the horizontal direction? So domain of XER, I would say. Let's have a look at their range. With the board in that center point. The range of the graph, would you agree it's going upwards infinitely and downwards infinitely? So YER. It's easy enough. What are some other features of these kinds of graphs? So let's think. According to the first one, you could get a point of inflection. Could have a point of inflection. E.g. for y equals x cubed minus 2. That would have a point of inflection that would kind of look like this. Have a little point of inflection there. It could have two vertices, meaning a maximum and a minimum, like in the other two examples. What did I just do there? Very weird word. Minimum. So we could have two vertices, a maximum and a minimum. Like in those two examples there, when basically when B and C are not zero. E.g., when B and or C are not non-zero values. So, like in those two examples we've got above there. What else do these graphs have? Have a little look. It's possible, have you noticed it's possible to have up to 3 X-intercepts? So do you see the one I've done here? We've got an X-intercept here, an X-intercept here, one here, and one here. So it's possible to have 3 X-intercepts. The first graph, as you can see, just has 1 X-intercept. That's when you get the form x cubed. The second one has 3 X-intercepts, and notice this last one has only 2 X-intercepts. And that's because one of the X-intercepts happens to also be a vertex. So it can have up to 3 X-intercepts. Have up to 3 X-intercepts. Has a Y-intercept, obviously. They all seem to have just one Y-intercept. Have one Y-intercept. You might have always realized the highest power of x is a 3 because it's x cubed. Highest power of x is 3. Is there anything else? I think we've kind of got most of the things. Can't really think of anything else interesting. If you can think of anything else interesting, you feel free to jot it down. Let's move on. So as you may have already worked out, a cubic function is one where the highest power of x is a 3. Whereas a quadratic, would you agree that the highest power of x in a quadratic is a 2? And in a linear, the highest power of x is a 1. So let's practice just some algebra. Example, by expanding out the following, show that they are cubic functions. So we're proving that they have an x cubed term. It's pretty obvious that it will have an x cubed term, but let's practice doing some pretty complex expanding. I'd suggest FOIL this part first, and then FOIL the next part second. So when you do that bit of green foiling there, just rewrite that, x minus 1, I'm going to colour code. So now the foiling of this, the last two brackets will get you x squared plus 5x plus 3x plus 15, which when you combine like terms there, you'll get x squared plus 8x plus 15. Just practicing basic foiling there. And then do this bit and do this bit. So a lot of expanding going on when you've got cubics. The top part expanded will give you x cubed plus 8x squared minus 15, and bottom ones, these ones here, will give you minus x squared. What did I do wrong there? Oh yeah, of course, I forgot it was 15x. It was plus 15x. I was thinking of the next part. So I'll just check that. Top one is x cubed plus 8x squared plus 15x, sorry. Now the bottom expanding will give you negative 1 times x squared, negative x squared, negative 1 times 8x, negative 8x, negative 1 times 15, negative 15. Combine like terms and we end up getting y equals x cubed, 8x squared minus 7x squared plus 7x squared, 15x minus 8x plus 7x minus 15. Just by coincidence it turned out that we got 7x squared and 7x, that's just a coincidence. So we could maybe say it's a cubic. It is a cubic as the highest power of x Okay. What I strongly suggest you do is write it out as this 2x plus 1, and then see it's x minus 4 bracket squared. Don't be lazy, because sometimes people make a mistake if they don't write it out like that. Actually write out x minus 4 all squared is x minus 4 times x minus 4. I would suggest, like before, FOIL the second part. Doesn't matter which two brackets you choose to FOIL first. I just find it easier if it's set up like this, because then the 2x plus 1 is at the beginning, which is nice when you're going to have to do the extra expanding in the later steps. Then we've got x squared minus 4x minus 4x plus 16. Don't forget a negative times a negative is a positive. 2x plus 1, x squared minus 8x plus 16. Top part expanded, we get 2x cubed minus 16x squared, and then plus 32x. And the bottom part expanded, we've got plus x squared minus 8x plus 16. Now let's combine our like terms. We've got 2x cubed minus 16x squared plus x squared, which you agree is minus 15x squared. 32x minus 8x would give us plus 24x, and then plus 16. So let's see if you agree with that. And then we should state the same thing as what we did over here in green. It is a cubic. That's what we're asked to prove. As the highest power of x is 3. Okay, they're done. Great. Next one, use axes intercepts only to sketch graphs of the following. So remember, at the x-intercept, at the x-intercept, y equals 0, and at the y-intercept, x equals 0. That's important information to use here. So I'm going to work out the y-intercept. I might just do it over here, because at the y-intercept, x equals 0. So the y-intercept is 0 minus 1, 0 plus 3, 0 plus 5, which of course is negative 1 times 3 times 5. And what's negative 1 times 3? It's negative 3. Negative 3 times 5 is negative 15. So we've got the y-intercept. Beauty. And now remember, at the x-intercept, y equals 0. So I'm going to be lazy. I'm just going to say this thing equals 0 at the y-intercept. Go straight to that. Save some space. So if that equals 0, so notice x minus 1, if that equals 0, x equals 1. X plus 3, if that equals 0, x equals negative 3. X plus 5, if that equals 0, x equals negative 5. So we've got our three x-intercepts and we've got our y-intercepts. Draw up some axes. Don't forget to label x and y, don't cut corners there. We've got x-intercepts at negative 3, negative 5, and 1. So let's go 1, 2, 3, 4, 5. Do it a bit evenly than I am. 3, 4, 5. Y-intercepts at negative 15, if you want to just mark it in. So x-intercepts negative 5, negative 3, and 1. And it's got to go through y-intercept of negative 15. Let's just have a little go at sense down there. Now let's draw our groovy little graph. So you can see it's kind of like, is it going to be that form or is it going to be that form? Don't write this one down yet. So for it to go through those and that point negative 15, would you agree it's kind of got to be going up? It's sort of from here. We don't know how high up it's going, that's fine. Through that. Otherwise, if you did it the other way around, like if you did it going down first, I'll just show you in yellow and I'll undo it. It wouldn't end up going through negative 15, so that's why I know the yellow one's wrong. The purple one's right, because it goes through our 3x intercepts and it does go through the y-intercept. So you need the y-intercept to decide which direction it's going. If you want, you can put little arrows there, you don't have to go. It helps. Okay, are we done? I think that one's done. Nice. because that's what we want to just use x-intercepts to sketch the graphs of the following. Next one, let's find the y-intercept. So the y-intercept equals 3 times 0 times 0 minus 4 squared. So 0 minus 4 squared is negative 4. Negative 4 times negative 4 is 16, but you're still multiplying it by 3 times 0, which is just 0. So you're just going to get 0 for your y-intercept. And at your x-intercept, we just set this one equal to 0. Actually, no, I'm going to do it back up down under here. Set the x-intercept here. So I'm going to write out 3x, x minus 4, x minus 4 equals 0. So we've got x-intercepts of x equals 0, x equals 4. We don't bother to write out x equals 4 twice, because, so if 3x equals 0, x equals 0. If x minus 4 equals 0, x equals 4. If x minus 4 equals 0, x equals 4. So the fact that it was doubled up on x equals 4 means that this x-intercept is also a vertex. So when it's doubled up like that, then that tells you that at that particular x-intercept it also happens to be a vertex. Like really vaguely, it's kind of going to go, whoop, do it badly there. Don't write this one down yet. Just doing it vaguely. It's kind of going to have a little turning point, for example, at that point, at that x-intercept. So now let's do a sketch of it. Quick sketch, and you might find we need a bit more information, but I'll just try to explain why first. X, y, we know our y-intercept is at 0, and we've also got an x-intercept at 0, that's interesting, and we've got another point at 4. So let's go 1, 2, 3, 4, 1, 2, 3, 4. So we've got another x-intercept here, and I've already plotted the y-intercept. That happens to be the same as the x-intercept. So a bit tricky, we don't know. We know it doubles up at x equals 4. By the way, I probably should have marked in the numbers here. Negative 5, and 1, negative 3, negative 5. It's probably important that I mark those in. Same with this one. Let's call this one 4. Negative 4. We know it doubles up at that second vertex at x equals 4, at that second intercept, x equals 4, happens to be a vertex as well. But don't draw this yet. We don't know whether or not the graph's kind of going like this, or use the graph going like this. So there's only one way we could probably do that, is we could potentially just plot another point. So we could plot a point when x equals 1 is an easy one to sub in, because if we get a positive value, we know it's going to be like the yellow one. If at x equals 1 we get a negative value, we know it will be like the purple one. I'll just undo those. Nice. So we need more info, as I said. So at x equals 1, what's our y got to equal? Y must equal 3 times 1, 1 minus 4 squared. I'm just using the equation above. 3 times 1 is 3. Negative 3 squared. Negative 3 squared is 9. 9 times 3 is 27. So it's positive. So that tells us that it's kind of going more so up like this. So it's got to, because it's going to be 27, like it's going to be a positive value. So it's kind of going up, some turning point here, and remember here it's got to be a turning point because it got doubled up. So that's kind of a turning point. I didn't draw it very nicely. Let's go back up, through there. Also, I'll try to make it a bit more of a sharper turning point. So there's got to be a vertex at x equals 4, and it also has to be an x-intercept. And it's got to go through the other blue point at 0, 0, and when x equals 1, y has to be positive. If it was negative, it would be going in the opposite direction. If you want to put arrows on it, you can. Don't need to really. So notice I had to do this little part here to be able to work out which direction the graph was going. So that's a strategy you can use too, if you're a bit stuck. Just plot another point using the equation you're given. Next one. Example, find the form. So we mean the equation, like y equals 3x squared plus 4x minus 2, of a cubic function for the following. So instead, what we've done is, on the previous one, notice we gave you the equation, we wanted you to find the graph. So on this one, instead we're giving you the graph, we want you to work backwards, do the reverse process to go back to the equation, as I said in the little hint. In other words, use the X-intercepts. Sorry, what's that? So in other words, use the X-intercepts to do the reverse of what you did on the previous page, and use the Y-intercept to see if you need a multiplier out the front. Like, once you've got the X-intercepts, to get the Y-intercept, you need to have made sure everything was multiplied by -1 or by 2, or is just using the X-intercepts alone getting you the correct equation according to the Y-intercept. So here's our little X-intercepts. So we're, at this point, maybe assume it's kind of like 1 here, -1, and that's at -2. The Y-intercept is at -2, as you can see. Alrighty, I'll scroll down a bit. So let's write out what our X-intercepts were. So X-intercepts were x equals -2, x equals -1, x equals 1. What could that have been when it was in the brackety form? It would have been x plus 2, x plus 1, and x minus 1. That's what our y kind of equals at this point. Alrighty. So what we can do is test out using the y-intercept. So for the y-intercept, what is the y-intercept? X equals 0, 0 plus 2, doing a y-intercept check. 0 plus 1, 0 minus 1, which equals 2 times 1 times -1, which is -2, which matches our y-intercept. So, which matches our y-intercept. Intercept, so no need for a multiplier out the front. Like, we don't need to multiply. If the y-intercept happened to be +2, then we need to have -1 out the front like that. But it turned out turned out that it's not +2, it's -2, so we don't need a negative at the front or any other number. No need for a multiplier out front. So our equation, we can feel more confident now that our equation is y equals what we just had, x plus 2, x plus 1, x minus 1. Fantastic. Now let's do our second one. So we've got y-intercept to +2. We've got x-intercept at -1 and 2. And we also have a vertex here. So we have a vertex here too, which, remember, that means that bracket gets doubled up. Our y-intercept, as you can see, our y-intercept is just here at 2. So y-intercept equals 2. Let's write out our x-intercepts. X equals -1, x equals 2. So because there was a vertex at -1, that means that that bracket, which would have been +1, gets squared. The other bracket is x minus 2. Now what we've got to decide is, using our y-intercept test, does there need to be a multiplier at the front? So y-intercept test, x is 0 at the y-intercept, x plus 1 squared, 0 minus 2. 0 plus 1 is 1, 1 squared is 1. 1 times -2 is -2. But notice our y-intercept needs to be +2. So as our y-intercept should be +2, we need a multiplier of -1. We need a multiplier of -1 out front. So we need to write something like y equals -x plus 1 squared, x minus 2. It's not wrong if instead you wrote y equals -x minus 2. plus 1 squared. They're the same thing. If you are a little bit unsure still, you could check it. Try subbing in at x equals 1 and see if you get the vertex, because we know this coordinate here, don't we? Notice we've got a little coordinate 1 and 4. We know that the vertex is 1 and 4. Oh great, it's frozen. I'm just going to have to pause, save and close it. There we go, we've just opened it again. So our vertex, you can see here, our vertex here is 1 and 4. That's what that vertex is. It's messy, so I'm just going to do that. X is 1, Y is 4. So we can use that to check if you want. So you can check at x equals 1. Do we get the answer of 4? Y equals negative 1 minus 2, 1 plus 1 squared equals negative 1, 2 squared. 2 squared is 4. 4 times negative 1 is negative 4, and then times the negative at the front is positive 4. Good. So we've checked. That's great. That it does match the vertex. Next one, have you noticed that this kind of graph, it's not the regular kind of roller coaster time? So remember, when it's in this kind of form, we've got to think of a point of inflection. So this little thing here, it's a point of, I have no idea why this happens to that point. There's more stuff there. So that's a point of inflection. Point of inflection, so it's in the form of y equals x cubed, and it's going up like this, it's not going down like that. So it's positive x cubed, otherwise it'd be negative x cubed. Point of inflection has moved upwards because the point of inflection is at 0, 1. So the equation of this graph, it's easy, it's just y equals x cubed. So x cubed is a regular graph, but normally its point of inflection would have been 0, 0. So if it's shifted up, it's just x cubed plus 1, because everything's just shifted up by 1. And then we can point this out and make another note of that. As the point of inflection has shifted up 1 unit. One. The next one, this one, it just didn't give you the graph, it just said it has x-intercepts, so only 2 x-intercepts, so there must be a bit of doubling up. So x equals 3, x equals 1, actually no, not x equals 3, x equals negative 3. And x equals 1, and it was, what am I saying there? I'm thinking of the brackets. So it's late afternoon and I'm tired. X equals 3, x equals negative 1. So in the brackets, that would have been x minus 3, that would have been x plus 1. It has a y-intercept at negative 18, we also know. And it also has a point 1 and negative 16. So one of these got doubled up. Is something that you might want to make a note of. So 1 must be a vertex. So 1 must be a vertex, and therefore squared. So the bracket would have to be squared if it was the vertex. At this point you might not really know which one, so have a little bit of a gamble if you want. So I'm going to guess the first one squared. So let's say x minus 3 is squared. And then you've got x plus 1. The reason why I'm choosing to do that is I noticed that the y-intercept is negative 18. And then sort of like squaring the 3 is going to make a 9, so then I'm predicting that they're probably going to make us double it to get 18. Because if I squared the other one, we still could get to 18, like we could have a 6 out the front, but that seems like a lot of work. So I'm just going to have a go guessing it's this one. Alrighty, so notice if that was the case, and the y-intercept is at negative 18, so think, if you sub in x as 0, 0 minus 3 all squared is positive 9, 9 times 1 is 9, so to make a y-intercept of negative 18, we'd need a multiplier at the front of negative 2. And this is to make the y-intercept match what was given in the question, which was negative 18. So it's possible it could be this. Let's check it with the coordinate that they gave us. Check. So the coordinate they gave us is 1 and negative 16. We're going to sub that in for x and y into our equation above and see if it works. Because remember, that's y equals, if you're not sure. So y equals that. Let's try subbing that in. So negative 16 equals, according to this, negative 2, open brackets, x is 1 in this case, 1 minus 3 squared, and then 1 plus 1. 1 plus 1. No square on that one. Let's see if this works out. Negative 16 equals negative 2. 1 minus 3 is negative 2 squared times by 2. Does that work out? Let's see. Negative 16 equals negative 2 squared. You've got to do bed math, so you've got to do the squaring first. Negative 2 squared is 4. 4 times negative 2 is negative 8. Negative 8 times positive 2 is negative 16. Yay, it works. So we can feel, if you want to do another test, you can try to find another point, but we can feel reasonably confident that it's negative 2, x minus 3 squared, x plus 1, oops, x plus 1. I might have also, not wrong if you wrote it as this, negative 2, x plus 1, x minus 3 squared. So long as the square's on the x minus 3. Make sure the multiply's out the front too, or else it looks a bit weird. And we're not quite finished yet. Let's quickly save this. One more page. So the graph below has the equation y equals x cubed minus 3x squared plus cx plus d. Find the values of c and d. So if they just showed us the y-intercept on here, we could just plug that in for d, but they don't. So I would suggest find the y-intercept first by using the x-intercepts. Because don't forget, d is the y-intercept. So let's find d first. Y-intercept first. Using the x-intercepts. What are our x-intercepts? Our x-intercepts are negative 4, 2, and 5. So let's write that out. X equals negative 4, x equals positive 2, x equals positive 5. Let's put that into the brackety form. X plus 4, x minus 2, x minus 5. It's funny. Can't remove it. Yeah. I think in here it's alright. Now let's try finding d. D will be when you sub in 0. D equals 0 plus 4, 0 minus 2, 0 minus 5. Which equals 0 plus 4 is 4, times negative 2 is negative 8. Negative 8 times negative 5 is positive 40. So we've just found d. So our equation so far, going back to this thing here, our equation so far will be y equals x cubed minus 3x squared plus cx plus 40. So we've got a bit of more information here. We know this coordinate here, and we can sub in it for an x and a y, and we can use it to work out the c of x. So use the coordinate 120. That'll be x, that'll be y. to find C. Let's sub that in. So y is 20. So 20 equals x cubed. It's like 1 cubed minus 3. X is 1 squared plus c times 1. That's the x. And we know it's plus 40 at the end. So 20 equals 1 cubed, which is 1, minus 3 times 1 squared. 1 squared is 1. That's 3. So minus 3 plus c plus 40. So 20 minus 1 plus 3 minus 40 equals c. So would you agree now that c equals 20 minus 9 is 19. 19 plus 3 is 21. 21 minus 40. Hang on, what have I done wrong here? 20 minus 1 is 19. 19 plus 3 is 22. 22 minus 40 is negative 18. So we've just found our two answers. C equals negative 18. D equals 40. If you want, you can test it out by, plugging those in to your equation and see if you get matching points. If you've got a graphing calculator, you can check them by graphing as well. Remember, you can graph and you can trace all these sorts of things. Next one, find the inverse function for the following and sketch it on the same set of axes. There you go. Remember from previous page, we know this equation is y equals the next cubed version, x cubed plus 1. So to find the inverse function, remember we swap x and y around. X equals y cubed plus 1, and then we transpose. So x minus 1 equals y cubed, and then to find y by itself, we cube root both sides. Cube root of x minus 1 equals y. So don't forget, we like you to write it like this. The inverse function therefore equals the cube root of x minus 1. Find the inverse function of the following. That was one of the things we had to find. And sketch it on the same set of axes. So you could try having a little vague look at it on a graphing calculator. Let's practice graphing because we haven't done that much this lesson. I'm always checking my things with graphing where possible. If it's non-calc, you can't do it, but if it's with calc, you can. So we're going to graph the cube root of x minus 1. So it's going to be control that thing. So it's the cube root of, let's type in x minus 1 here. Enter. Yep. So see, it looks kind of like that. So notice that kind of like the X-intercept is now the same value as its Y-intercept, and its Y-intercept is now the same value as its old X-intercept. And if you're not sure what I mean, kind of like that. So it's kind of like down here now. So we can kind of do a little quick sketch of it. It's going to be very rough, sorry. So remember it looks like that. It kind of goes down like this. It's a very vague sketch of it. Another thing to just bear in mind is inverse functions. When you graph the inverse functions, they should be reflected across the line y equals x. What is the line y equals x? I'll just put a dot 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 line going through y equals x. That's y equals x. The inverse function should be symmetrical, or mirror images, sorry, around across that y equals x. So my y equals x line is a bit dodgy because of this funny board. That the inverse function, they should be mirror images across that line y equals x. Maybe I'll just undo that and I'll do it with a nice special line tool. Oh, great. Okay. Undo. Do it again. These boards don't like to cooperate. They keep going uncalibrated. Just undoing all those dots. Let's use a little line tool instead. Might point it out a bit better. here's the line y equals x. I'll do it roughly. I'm cutting through there. So here's the line y equals x. So inverse functions are reflected across the line y equals x. So inverse functions are the original function, which in this case is red, the original function reflected across the lines, back to symmetry, remember back to symmetry, across the line y equals x. That's a special thing to do with the relationship between the original function and its inverse function. The inverse function happens to be the original function, but reflected across the line y equals x. So the x-intercept on the original function should become the y-intercept on the inverse function, and vice versa kind of thing. Alright, I think that's kind of the end of it. I was going to also just show you an example of how to check ones like these by graphing. So imagine your final answer. We kind of got, we find the values of C and D. So we're checking, okay, if C is 18, D is 40. C is, sorry, was it negative 18? I think it was negative 18, wasn't it? Yeah, it was negative 18. So, sorry if that's annoyed you all this time. Let me just fix this. So in my working out, you can see it says negative 18. So let's just fix this to say negative 18 as well. Can happen when you type. Okay, so we're saying negative 18D is 40, so I'm going to graph that top function and just see if I happen to get something that looks similar. And because remember, we can do things like graph trace. We might need to adjust windows too to be able to see it, so this is good practice. So let's do a little graph. So I'm going to enter in this x cubed, so x to the power of 3 minus 3x squared. And then it should say it's plus, C is negative 18, so negative 18x. And then D is plus 40. Always have a look and see did what you type in happen to be what you hope to type in, just before you press enter and graph it. So here's a function. We can't see the vertices, so you could always adjust the window. So you can go menu, see window zoom. I prefer to do it manually rather than just clicking the zoom in, zoom out button. So negative 4 to 5, negative 10 to 10 is fine, but I can't see the top and the bottom very well of the graph. So I'm going to change this one to something like negative 20. You can do even lower if you want, because this is the minimum value of the y, and we want it, this is where we want, now the maximum is what we want it to go up to. So negative 20 to 20. Still can't see the top, so you could, if you wanted to see the top, you would have to now make the y max higher. Maybe it should be something like 50. Oh gosh, what did I just do there? I messed something right up. I typed in something weird. Oh, that would be it. 50. Should have had there instead. No, it's better. I still can't see it. If I want to keep seeing it, I just need to keep making that y max, where it goes up to, higher. I'm not bothering to change my y min, because I can already see the bottom of the graph. I can see the bottom turning point. Now I can see it all. That's in case you wanted to be able to view it all. But if you want to trace it and find what the values of the y-intercept is, the vertices if you need them, the x-intercepts, then you can do this menu, trace, graph trace. And then you just arrow left and right. So see, here's my maximum, tells me the coordinates of my maximum in case I needed it. I'm just checking my x-intercepts. So see when it says zeros, this one's telling my x-intercept is at negative 4. That's great. If I needed my y-intercept, I'd just keep arrowing right to the y-intercept till it pops up. Y-intercept, you can see, is at 0.40. That's great. That's what we want it to be. X-intercept at 2, that matches our graph. We needed the vertex. See, it's sort of, as you scroll, it kind of goes down to show you what you're trying to look at anyway, which is quite nice. The old calculators didn't do that. We don't need the vertex in this question. 0 is at 5. Cool. So that's a little way that you can check your graph, and kind of like you can adjust windows if you need to, and graph trace. It's a really neat little feature, and it's easy to use it on these TI Inspires than it used to be on the old calculators. So thank you very much, and that's the end of cubics.